In case you ever wondered, this is what it looks like when you rapid an M42 Cobalt drill into D2 tool steel at 6,000 RPM. It looks for all the world like the drill partially liquefied before it went off to wherever it went, and I had no idea that could even happen, but apparently it can. Welcome back to Cloud 42. I'm James. If you've been around the channel for a while, then you will remember when I made this. This is a hand PC board nibbling tool for separating PC boards out of larger panels, with some 3D printed parts and a pneumatic cylinder to turn it into a foot pedal operated tool so that I can quickly separate large numbers of PC boards out of their panels. And this tool has been working great, and it is still working great. I've cut between 1,000 and 2,000 PC boards with it, and I've been very happy with it. However, there are commercial tools that do this that are even nicer, and they're normally pretty expensive, but one came up on eBay recently, and I grabbed it. Partly because it'll allow me to use different width blades for different PC board panel layouts. And that's what we're going to do today, is actually make a blade the right thickness for the panels that I cut. But the other reason I wanted it is because it's a tool and I want to own them all. Before I jump in here, I wanted to show these. These were sent in to the channel by Robert. And Robert, thank you very much. These are cork coasters with my logo lasered into them. And these things are great. I will definitely be using these around the shop. For one thing, I'm not going to leave any more rust rings on my welding table. Perfect. Now, this is the separator tool that I made. And you can see this is just a simple little hand nibbler that was sold as a PC board separator for hand use. But since I had thousands of boards to cut, I 3D printed this framework and mounted a pneumatic cylinder to make this a foot pedal operated tool. If you haven't seen that video, I'll put a link up in the corner and you can go check that out if you're interested. But this is the commercial alternative, or I guess this is the alternative to this commercial tool. This is called a Sep3. This is made by Olamef, and it consists of a hooked blade between what they call the matrix, which is a couple of steel anvils that it pulls down between, and it's all mounted on top of a pneumatic cylinder. They've got a pressure regulator here so you can hook up a foot pedal and operate it. So very simply, it's just an air pressure actuated device, and I can just put some air pressure with a blowgun into the ports, pull it down, press it back up. So it's just a double acting cylinder, and you slide the PC board with the little mouse ear to be cut right here, and it just snips it off. You have that with a foot pedal. You can just go chunk, 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 chunk through the whole board and cut them off rapidly. So I've already looked at this, and this is a used tool, but it looks to be in very good shape. Let's tear it down and take a look at the blade. The matrix is in two parts, and they're just these little pieces of angled steel. You can see there's definitely some wear there. This is much softer than the blade, so this is the part that's going to wear, but in general, a little bit of wear shouldn't hurt anything. We might try to dust that off with a grinder. And the other half looks very similar. And then the blade itself is just held to the piston with a single screw. And that is the blade. Let's see, this one is 1.35 millimeters thick. That is a little bit thin for my use, so I'm going to need to get a thicker one for the PC boards that I cut. Now, you can actually buy these from Olamef. They're $100 or more per blade, and I'd like to get a couple of different thicknesses. So it might be worth actually looking into making these in the shop. So I did a little bit of figuring, and I figure for materials and time and tooling, we can probably make these for less than 10 times that price. So why don't we go ahead and do that? I've got some material. This is the material I'm going to use. This is D2 tool steel. I've tested the hardness of this blade. I've got my hardness testing files here, and we'll just grab the HRC 65, which is the hardest one that I have, and it just glides nice and smoothly, just makes a shiny spot on the surface, doesn't cut at all. So these are very, very hard. They're up around 65 HRC or harder. And this material should easily be able to reach this. This is D2 tool steel. And so when this is hardened, it should be very, very tough. It should be very abrasion resistant, which is important because the FR4 PC board material this is going to be cutting is going to be very abrasive and it's going to wear, and I want it to hold its edge. So this material should be suitable. And I think we'll just take it over to the CNC mill, cut the parts out, heat treat them, and then grind them to thickness. Now, I have never worked with D2 tool steel before. From what I've read, it is actually fairly rough to machine. Machinability of around 27%, which is probably one of the tougher materials that I've worked with in the shop. Though I think if we have good carbide tools and we get the speeds and feeds right, so we're not rubbing and we're not being too aggressive, we really shouldn't have too much trouble. We will see. I am going to run the high-speed spindle that I put on my G0704 CNC mill, and so that might be a little tough to reach the slow speeds I need for drilling so I don't burn up drills. But for an 1/8 inch carbide tool, which is probably what we'll use to cut this out, it should be no problem. I have the part already modeled here in Fusion 360, and I'm not going to go through the entire process, but I will show you a couple of tips that make drawing parts like this a lot easier. Now, I actually took a photo of the part and imported that, and then drew the sketch on top of that photo. And that's really easy to do. Just click New Design, Insert Canvas, select my photo, and then select the plane that I want that photo on, and it imports it. But it's not the correct size, and we can fix that by going over here to Canvases. We'll right-click on the canvas, say Calibrate, and then we can drag a dimension or come and click 2 points that are a known distance apart, throw a dimension on it, and then enter that dimension. So I know this is 76.5 millimeters, and now it has scaled that canvas to that size. So now I can just come in and say Create Sketch, select the same plane, hit L for line, and I can just start sketching out my part. And I'm just going to do this roughly. We'll come back later and put actual dimensions on it. But I can then, roughly get my part to the right shape. And, this is fine for lines. I'll come back and put dimensions to get them in exactly the right place. But this is great for curves. So I'll do a 3-point arc here, click these 2 points, and then I can just adjust the arc to fit the photo. And so then when we're done, we end up with a sketch that's fully dimensioned. In this case, I followed the photo to get it in roughly the right place, and then added the dimensions to make it exact. And then from that, we can just extrude the part, and we are then ready to machine it. Now, to machine this part, we'll just go through the simulation here. I didn't want, this is pretty tough material, and I'm going to be using a pretty small mill, so I wanted to make sure I had good entry points. So we drilled 3 holes first for entry, and then just mill out the perimeter with an 1/8 inch end mill, and then come back and bore and contour the insides of all the holes. So this should be a pretty straightforward part to make. Let's export the G code and take it out to the mill. Got my stock cut to length. The total part's about 3 inches. This is just over 3 inches. And we need to find a way to hold this. But since I need to mill around the entire perimeter of it, we can't really hold on to it with clamps. We can't really put it in the vise without doing something really exotic. So what I'm going to try is super glue. And I've got a piece of aluminum here that I've already faced off. I'm going to wipe down all these surfaces with 99% isopropyl and make sure there's no skin oil on there, and then we'll just stick it down with super glue. I already cleaned this once and then I came in here and touched it. And this is 99% isopropyl alcohol, which I have hanging around all the time because it's used for 3D printing. Give it a second to flash off. And then I'm just going to use Loctite 420. This is a thin CA adhesive. And I'll just put on way too much, put the part down, and then weight it down and let it set. And to weigh it down, I'm going to use a 246 block. And that should be plenty heavy. We'll let that sit for a few minutes and set up, and then we'll machine it. Okay, it's been about 10 minutes. Let's see how we did. I didn't glue my 246 block to it. That's good. And it's not even slightly stuck down. Okay. This is not working. Let me grab some accelerator. Let's do this again with the accelerator this time. So we'll put some super glue on there. And I've got this Loctite 7452 accelerator, and I will put that on the opposing part. And we'll try that again. Okay, that has already grabbed tighter, and I'll go ahead and shoot some accelerator around the edges. And I will go ahead and weight that down, and we'll give it another 10 minutes. It should be fine this time. Let's see if we did any better with the accelerator. I'm pushing on this as hard as I can with my thumbs because I really want it to break off now if it's going to break off. It feels all right. Let's go ahead and zero up and start milling it and see what happens. Oh, that's interesting. You can see the outgassing from the chemical reaction actually leaving marks on my 246 block. I'll have to stone that. Okay, the first tool in the program is a drill, and that's tool 101. And we're just gonna put some holes in this and where the internal cavities are gonna be milled to give the end mill a fighting chance to get in there. Set up the mist so it's got half a chance of getting in the right place. And we'll give this a shot. Now, unfortunately, because this is such a high-speed spindle and because we're milling such a tough steel, I've got the spindle running relatively slow. I think it's going to have enough torque to deal with this, but there's only one way to find out. Let's give it a shot. Okay, that looks all right. Now the tool that's going to do the most work here is an 1/8 inch 4-flute carbide end mill. This one is a coated end mill from Lakeshore Carbide, and we're going to give it a shot. If anything's going to blow up, this is where it's going to go wrong. I'm going to be running this at 6,000 RPM, which is about 200 surface feet per minute, which is probably still a little fast for something tough like D2, but I think it's going to be all right as long as the super glue holds and as long as I've got my feeds and speeds right. We should be able to cut this. But again, I should just stop talking and do it. There's only one way to find out. And sure enough, there we go. The super glue did not hold. Okay, well, let me regroup and see if I can figure out another approach here. Okay, I tried something a little bit different this time. I used Loctite 414, which is a little bit thicker, and I cut some grooves across the aluminum block to give the excess squeeze out someplace to go. I used the accelerator and stuck it down, and it just grabbed a lot quicker. So I'm hoping that this stuff works better than the 420, but there's really only one way to find out. We'll just give it another try, and if it flies off again, we'll figure out what to do about that. And right there at the end, while it was going up, after the last cut, it lost steps on Z. Crazy. Okay, let's see how big those holes are. Looks like the round holes came out about 233, yeah, 232, let's call it. And a small hole in the center for the screw. Call that 161. I will go and modify the program, export the G-code, and we'll just run those external perimeters on those holes again to open them up about 6 thou, so take 3 thou off the wall. And that's all just going to be tool deflection here. But I will do that, and we will give it a run. In previous videos where I've said, I'll just go back and take a few more thousandths off one of those features, I've had people ask in the comments how I do that, so I figured I would show that. So I've got my setup here in Fusion 360. Here are my operations, and I have already posted this, and so I have my NC program here. It happens to be called NC Program 2. It was just the default it was given. And so if I modify these and then repost, it'll regenerate this program. And that's not really what I want. I really want to create another program that just does the recontour. So I'll come in here on this main contour. I will right click and I will say duplicate, and it will create a second one, which I will call recontour. And then we will edit that. First thing I want to do is come into the geometry, and I'll control click to take off the perimeters I don't want to cut. I just want to cut these two holes bigger. And so we'll go over here to the passes tab, come down to stock to leave, and we'll axial stock to leave will set to 0, and then radial stock, I want to make this and I want to take an additional 0.003 off of each wall, so I'll say minus 0.003. Okay, and now that will generate an operation that will just take 0.003 off of that wall. So now I can come up here and say post process, and this will create a new numerical control program, and I'll call this 1002 recontour. And over here on the operations tab, I have, because I had that selected when I chose to create the new program to post it, it's selected, but I can select exactly which operations I want in this, and I can leave just that one recontour operation there, click post, and it will then generate a new program that has only that one recontour operation. And then that recontour operation appears up here as a new NC program, which I'll also call recontour. And so now I can go back in and modify that if I want and regenerate that program. If I open up the initial program, you can see that this new operation that was added, recontour, is not turned on as a part of that. I could turn that on, or I could modify or do whatever I want with this. And so generally what I'll do is I'll create the recontour. Once I get that dialed into size and just redoing that one operation until I get what I want, then I'll go back and modify the original contour with the same parameters and repost the original program so I can use that to make more parts that are already the right size and don't require the recontouring. Should be looking for 238 on this hole, and we're actually a little bit over, so took out a little bit more of the spring. How far over? Yeah, about 239, so we're about 1 thou over there. The small hole should be 168, and it clears that easily. It's just a clearance hole for a screw. 169 doesn't quite go through, so we're actually in just about the right place. Okay, that is the part milled to size. Okay, now that the part is made, the last thing to do is to separate it from the super glue. And to do that, I've got a torch, and we'll just heat it up, and that should break the super glue bond, and it should come right off. Really know how much is going to be needed, but that's it. And these parts are the result. They look pretty good. I'm pretty happy with these. Now, I cut the one on camera and you got to see that, and you got to see that I had a little bit of trouble with the super glue, and I continued to struggle with the super glue. I think this one popped off twice. And if you look very closely, you can see that this center hole is very slightly out of round, and that's because I drilled the holes and then it broke free, and I put it back on and finished the machining. And there was enough margin everywhere except that hole, but that's just a clearance hole for a screw, so it doesn't matter at all. And then you can see that I cleaned out the corners on these so that they are nice and sharp inside with a very small radius, and they match up to the original part very, very closely. In fact, it's pretty much a perfect match, except for the thickness. So these should now be ready to go. I did have one mishap. If you may have seen this on Instagram. This is a little scrap of one of the parts. And what you see there embedded in that is an M42 Cobalt drill. I had it spinning at 6,000 RPM, started the CNC program, and it was the wrong code. I actually had the code from the recontour still loaded when I went to make the second part. And so it tried to plunge down thinking it was a short end mill, and it was not. It was a long drill, and it has embedded that drill, and actually it looks like partially liquefied it into there, and that is now a permanent part of this. Didn't penetrate the tool steel. I have never seen a drill do that before. I would have expected it to just snap off, which it eventually did, but not before really mangling and embedding that M42 Cobalt material into this part. I'm truly impressed with that. And all I was able to find in the end was the tiny little stub of the drill that was still in the drill chuck. Everything else is either in here or completely gone. Now, to heat treat these are going to be treated at 1850 Fahrenheit. That's pretty hot. I don't have a lot of excess thickness here to lose to oxidation. I don't want to do a lot of grinding, so we're going to enclose the parts in stainless steel foil. And this is just a type 321, so technically it's low temperature, good to 2000 degrees Fahrenheit, which will do for this. And this, just got this from McMaster-Carr, and comes with a little seam roller. Nice. Now, if and or when you work with this stuff, know that it is very, very sharp. Okay, I'm just going to go squeeze the end of this in the vise. Okay, that gives me a nice, neat little packet. It's sealed on the sides, and the end I've bent up at about a 40-degree angle, maybe a little bit more, and that'll give me something when this is in the furnace that I can grab onto to take it in and out. This is my heat treat oven. This is a HotShot 360 made by Stan over at Bar Z Industrial. This is one of the early models that he manufactured in his shop prior to these being sold by American Rotary under the American Kiln name. This one has the N480D, which is the ramp and soak controller, and I have it pre-programmed to ramp up to 1400 degrees for a preheat. Over the course of an hour, then it will soak at that preheat temperature for 30 minutes. Then over the next 30 minutes, ramp up to the heat treat temperature of 1850. It'll soak there for half an hour and then power off. So the entire process is, what, a 2.5 hour heat treat cycle. Because these parts are so thin, that's probably overkill, but that's quite a bit faster than the 5 to 6 hour cycle recommended by the manufacturer. Now, I've got the oven cold, and I will just put the parts in here on a tile where they'll be easy for me to grab and get out later. And then we'll just start the program. Enable program, yes. Run, yes. Go, and enable the heat. And the bottom temperature is a set point, so that's 62, 63, 64, that's slowly ramping up, and then the PID controller will engage the elements and track that curve, and we'll come back in a couple of hours when this is ready to quench. Now D2 is an air quenching tool steel, so you can just pull it out and just let it cool in still air and it will harden. But I'm going to use a technique called plate quenching. I've got a couple of pieces of aluminum. These are 1.25 inches thick. And so there's quite a lot of aluminum mass here, and I will pull the aluminum foil packet out, or the stainless steel foil packet out, still in the packet, set it here, set the other one on top, and clamp it down. And that will do two things. One is it'll suck the heat out rapidly without ever exposing the parts to air because they'll still be in the packets. And the second thing is, because the parts are clamped between two flat surfaces, it'll be very difficult for them to warp. It'll hold them in place. And this is a common technique that's used for knife making. This is all brand new to me. I haven't done this before, so we will see how it turns out, but I'm hopeful. I've got a thermocouple taped here to this top block of aluminum just to see how warm they get. And I've got that on my meter here. And so when the time actually comes to quench, we can see how much the temperature rises on the aluminum parts. The aluminum is going to stay pretty much one temperature because it conducts heat so well. So this will give us a good idea of just how much heat's being sucked into these. I'm guessing the temperature's not going to change on these much at all. Okay, this has been running now for about 2.5 hours, and we're at 1850, and we've been soaking at 1850 degrees Fahrenheit now for about 30 minutes. Okay, we'll clamp between the blocks, and you can see the temperature is already rising because aluminum is such a good conductor. Up to 80 degrees Fahrenheit already. And I can feel the heat going in there. The fan on the oven is going to continue to run even though we've turned off the heating. And that's because the fan is just cooling the electronics box. Okay, and now you can see that the temperature of the aluminum blocks is now starting to drop. I can just barely feel the warmth in it now. And so I think the quench at this point is pretty much done, but we'll give it a few more seconds. Yeah, even the foil here that's sticking out the side is cold to the touch. Yep, barely even warm to the touch. Okay, let's open it up. There are the parts. They look flat and they look straight. See how hard they are. Just for comparison, this is the material that we started with. This is the lowest hardness file I have, the HRC 40, and it easily is digging in and grabbing. But on the heat-treated part, yeah, that just skates. And here's the high end, the HRC 65. Yeah, and it just skates without digging in also. Okay, these need to be tempered and then they need to be ground to the final thickness. I'm going to temper these in the kitchen oven. I'll just put these in at 400 degrees Fahrenheit. Just set them both on a tile. Put that in the oven in a cold oven, or I probably put it in a warm oven. Temper these at 400 degrees Fahrenheit for a couple of hours, then just turn the oven off and let them cool, and then we'll be ready to grind. Now, I don't actually have a surface grinder yet, So I'm gonna head up to my friend Uchel's shop up at Woods Creek Workshop, and he's gonna help me grind these. That's not gonna happen today, but you will see that in a future video. Scratch that, you're gonna see it now. Through the power of prior planning, these blades are now ground and ready to go. It's been about a little over a week since I heat treated these, and in that time I flew up to Woods Creek Workshop and spent the day with Uchel grinding blades and eating noodles, and it was a great time. There is a video on his channel with the entire grinding process. I'll put a card up and a link in the video description. Definitely go check that out. You can see the grinding process, and while you're there, check out the other content on his channel, give him a sub. It's well worth it. I got to see in person some of the stuff that he's made, and the workmanship is just superb. It's well worth the subscription. Anyway, these are ready to go. Let's talk a little bit about what I learned in this process. First thing I learned is that D2 tool steel is very tough. I mean, I chose it because it's abrasion resistant, but that became really clear when grinding it. As long as you keep the wheel moving, you take in 2/10, maybe a 1/4 thou at a time, everything went great. But if you slow down, even for an instant, the wheel will grab, slow, and dig in. And this little beauty mark here is all the evidence that's left over that we couldn't completely grind out without going below thickness for one of those incidents. As long as you keep it moving, it grinds great. We were grinding without coolant with an open structure wheel. The parts were staying nice and cool, but you definitely needed to keep moving. The other thing that we learned is that this D2 steel, at least the way I heat treated it, had a lot of residual stress. I don't know if that's because of the plate quench, because it quenched so quickly or unevenly, as opposed to an air-cooled quench, which is what D2's usually intended for. But what we discovered is that as you grind material off of one side, the part started to cup to that side. So if in multiple passes you took it down 2 thou and then went and put that on the surface plate, you could put a 1 or 2 thou feeler gauge under the middle of it because it bowed that much. But then if you flip it over, suck it back down on the magnet flat, take the same 2 thou off the other side, it straightened back out. So as long as we took the material off evenly, the part stayed straight, certainly straight enough for this application. And since it warped a little bit as we were taking material off, I was a little bit worried that maybe it had only been surface hardened. But looking at this afterwards with the hardness files, this is the HRC 65 file, they still just skate beautifully over the part without digging in at all. So they were through hardened. There's no need to worry about that. Let's put this thing together and see how it works. That fits nice and neat on the alignment pins. Just a little bit of play, just like the factory original. Okay, that's the hook. Slide the matrix in here on both sides. And that should be that. Let me grab some air and make sure it cycles. Beautiful. I don't have any PC boards to cut. Let me grab something. What do I have that this would cut? This is a piece of PC board material, but it's not perforated, so it probably won't cut through this, but let's see. Nope. Oh, yes. Look at that. Oh yeah. I will definitely want to use this with a pressure regulator because that just sliced right through it, not even perforated. Okay, I'm going to call that a success, and I think we are ready to go next time I have a batch of PC boards to cut. Well, if you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Have you worked with D2 tool steel? Have you experienced warping? Do you use plate quenching? Do you use air quenching? Let me know your experience. I'm always looking to learn. And definitely go check out Woods Creek Workshop and check out the video on Uchel's channel and some of his other stuff while you're there. Thank you for watching.